Rankings out? Hopefully you have got some good results. Before we get into the OS of the day or anything like that, you probably have already seen this, but your midterms are now graded. There's no reason to panic. The average, I believe, after we take out all of the DNWs was something like 78.8 or 79. So if you were panicking, like, oh my God, I'm gonna fail, I don't think very many people did fail. I'm pretty sure most people got really, really great grades. So yeah, it's awesome. If you haven't had a chance to take a look at how you've done, of course, go onto the Crowdmark. We've posted a rough solution guide to Piazza, and you should take a look at that as well. Keep in mind when it comes to the solutions that we have posted, that it's very likely that we have changed or updated some of the solutions since when those were made during the actual marking. So just relax. If you see things and you're like, wait a minute, I lost a mark because of this, and it's like, well, there may have been more to the story, we just haven't recorded. If you're looking for a couple seats, there's a few over there and a few over there as well. Yeah, now remarks. If you'd like to issue a remark request, there's a form you're supposed to fill out. And I know the website would say, hey, you need to hand me a piece of paper. Let me tell you what happens if you hand me a piece of paper. I put it in my bag and I take it home. And then I go to, make supper or something, or answer an email. And my 5-year-old goes into my bag, takes out your remark sheet, and draws all over it. So, I mean, that could be a good thing if you like to see like dinosaurs drawn all over your stuff. But in reality, the best thing that you can do is to email it to me or email it to Allie. It is the instructors that actually handle the regrading, not the TAs, just so you know. I will not acknowledge that I have received your remark request until I actually perform the remark, and I will not actually do the remarks until the deadline has passed, and I will do them all together. So you've got just less than 2 weeks to submit your remark request. Once I have received them all, then I will remark them all, and regardless of whether we change your grade or not, I will let you know how your grade has changed or stayed the same, and I'll give you a reason why. So there will never be a mystery as to why you did or did not get any grades back. All right, any questions about the midterm? All right. Nobody's panicking, so I presume that's a good sign.
Listeners would love to say something. Am I still get a curve on it? Upwards?
Curve upwards? No. No, we're not going to curve upwards. Yeah, so we're not going to do it. All right, so the operating system of the day then is one that you might have heard of. It's called QNX. And here's the story of QNX. Once upon a time, a long time ago at the University of Waterloo, there were two gentlemen who were bored in trains. And they said to themselves, you know what would be really great if instead of making, a toy operating system for a bunch of trains, why don't we make a real-time operating system? And they were so bored in trains that that's exactly what they did. They went out and they made a real-time operating system. And they were indeed CS students at this very university. They go by the names of Gordon Bell and Dan Dodge. And they created QNX. Now, it was originally released in 1982. under the name of Quantum Software Systems, but it has since been acquired by RIM. Now, I'm always going to call RIM because that was their original name, but now, of course, they're called BlackBerry, and I'm not really sure what's left of them. When I was an undergrad, this was the University of RIM, and it was like, here's the university, and here's RIM, completely surrounding us. That's not the case anymore. So QNX is a real-time operating system. That means there are usually shorter quantums that are used for scheduling because we want the system to be more responsive. We're also going to put some guarantees, some timing restrictions. We want to guarantee that if there is an event that happens, that we respond to that event within a very short period of time. Why do we like things like real-time operating systems? Well, if you're trying to create a self-driving car, you kind of want to be responsive to events that are happening. Not, well, when we get a chance, when it gets scheduled. If somebody walks out in front of you, you need the car to stop immediately. You need that guarantee that the event is handled within a very short period of time. That's what real-time operating systems are for, is for things like self-driving cars, robotics, and so on and so forth. Now, in addition to QNX being a real-time operating system, it's also a microkernel OS, which means they put the absolute bare minimum of functionality into the kernel, and everything else becomes a user program. So in their microkernel, they have input redirection, not input handlers. They have timers, a CPU scheduler, and inter-process communication, but everything else, even the implementation of virtual memory, uses message passing within the kernel, so it does not actually live inside the kernel. So that's kind of cool. And one of the side effects of actually having a microkernel operating system is it means that the binary is actually really, really tiny. And when you have an operating system with a really, really tiny binary file, it becomes used for embedded applications. And embedded means that they actually will have the operating system on a piece of hardware, like on a chip, which makes it go even faster, and that's really, really great. Now, who has used QNX? So funny story, when I was an undergrad, I got exposed to QNX, and I saw it, and for no good reason whatsoever, I decided, hey, I'm going to use that OS for a year. It looked pretty. I know. Most people when they come to university, it's like, oh, let's try these new drugs or something. I know. I was like, ooh, operating system, that's pretty, I'll try that. So I used QNX for a while. But who had started out using it was the Ontario School Board. Because, Canada has this thing where a certain percentage of the products and media that is presented in this country must be Canadian. So we started out using it in the school board, but actually where QNX has become really powerful is in things like industrial applications, the automotive industry, and in navigation systems, and I cringe at the word infotainment systems. Carrier grade routers that are the big routers that are like the size of fridges that would be at like Rogers or something. And it's actually, QNX at the last count was used in over 56 million vehicles. So this is actually a very, very common operating system when it comes to things like cars. All right. You don't want Windows driving your car, right? That would be bad. And to be fair, you might be like, well, if you don't want Windows, I'll just get Linux to do it. No, you don't want Linux driving your car either. Panics happen. All right. So we left off, and I know you probably don't remember. I don't either. We left off talking about virtual memory in the kernel. So we've talked for a while now about the fact that we want our user programs to actually live in virtual memory. And there are multiple reasons why we do that, one of them being security, another one being isolation, and good abstract design. It's really nice that the program doesn't need to be aware that other programs exist. It sees a range of virtual addresses, and it thinks that based on the range of virtual addresses it sees, it has all the RAM to itself, isolated completely from everybody else. But it would be really nice if also the kernel of the operating system also ran in virtual memory. And here's the problem with having a kernel run in virtual memory. The kernel is also responsible for implementing and managing virtual memory. So while the operating system is booting, how do you actually have the thing that is responsible for managing virtual memory run in virtual memory? And we call that a bootstrapping problem, and we actually tend to solve that with an architectural solution. The other problem, of course, that we have with having your kernel run in virtual memory is a sharing problem. So it is, as you probably noticed from A to A, if you've hopefully started A to B, there is this need to get data from the user process into the kernel and then from the kernel back into the user process. Now, if the kernel was using the exact same virtual address range as the user program, then how would I know from which address space I was going from and to if everything is a virtual address and they're all the same range? I have no way of doing it. So I need some way of letting the kernel have access to everything that is in the user process's address space. And the solution to the sharing problem is actually really simple. We are going to take the range of virtual addresses and divide it in two. And we're going to say half of it is going to be for the user process and the other half is going to be for the kernel to use. And this is not just a solution that OS 161 is doing, this is actually a solution that pretty much every major operating system that exists is using. They use a 50-50 split of the virtual address range. Windows does it, Linux does it, Mac OS does it, they all do it. So what we have is the first in our OS 161, which uses, of course, 32-bit virtual addressing. The first 2 gigabytes has been set aside to be used for user addresses. And then the upper 2 gigabytes is set aside for the kernel's virtual address range. And the idea is now we see a virtual address, and based on that virtual address, I know exactly to whom it belongs. If I see something that is less than this, I know it is a user space address. And if I see something that is from here onwards, then I know it's a kernel address. Those TLB miss on panics? Yeah, you know how I know what code was running? This is why. That's how I knew what those addresses actually meant. Now, our address ranges don't overlap. And what it now looks like is that it looks like every process has a copy of the kernel's memory. There are not multiple copies of the kernel's memory. There is only one copy of the kernel's memory. It's just because the address range that it uses overlaps with every process, it gives the illusion that the kernel is a part of every address space, but it is not. There is only one copy of the kernel. Now, how does the address translation work? Well, what's interesting is when the CPU is in an unprivileged state, the CPU should only be able to perform address translations that correspond to the user process. However, when we change the state of the CPU to be a privileged mode, the MMU should now be able to translate both. But it is very important that our system is not able to translate a kernel virtual address when we are in an unprivileged state. Because if we can translate privileged addresses in an unprivileged state, then we are potentially giving access to the user program for private memory that belongs to the kernel, and that would be a very bad thing. All right. So, I'd like to take a closer look then at actually how OS 161's virtual memory is implemented. Now, we've already looked at the user programs and how they do their address translation, and of course, all of the code for that can be found in VM Fault, which is in kern arch mits VM wm.c. So let's look at the bigger picture then. So we have 32-bit physical and 32-bit virtual addresses. And interesting story, even though we are using 32-bit physical addresses, OS 161 and Sys 161, our emulator, can only actually use 1 gigabyte of physical memory. So even though you technically have, all of those addresses available in physical space, there is actually a limitation in the emulator that does not let you use beyond 1 gigabyte. If you're using a gigabyte of space in OS 161, what are you doing anyways? It is a toy. I'm confused. Did you forget to free things? Don't do that. All right. So we only actually have 1 gig of physical memory that's available. That's going to give us the physical address range from 0 to that number there. Now, taking a closer look then at the virtual address range, which also is a 32-bit addressed section, we have the first 2 gigabytes that is dedicated to being used by the user program. And we are calling that the KUSEG, the user segment. And then if we look at the remaining 50% of the virtual address range, what's really interesting is that instead of having one giant block to be used by the kernel, we have actually divided the kernel's virtual memory into 3 segments of its own. And you're probably thinking, oh, a code segment, a data segment, a stack segment. No, that's not what we're doing. We have 3 segments. They're called KSEG0, KSEG1, and KSEG2. KSEG0 and KSEG1 are both 512 megabytes each. And KSEG2 is 1 gigabyte. And the important thing that you need to know about KSEG2 is that it's not used. And that's not just something that's true about OS 161. I believe that's actually true about the R3000 as well. I was looking at the spec there a year ago, and I'm pretty sure that KSEG2 is just not used, not supported. All right. Now, what are each of these segments used for then? And in that case, we don't need to worry about KSEG2 because it's not used. But what's KSEG0 and what's KSEG1? KSEG0 is the virtual memory that is available for the kernel to use. So our kernel in OS 161 can only use up to 512 megabytes of RAM. Our operating system doesn't need that much memory. KSEG1 is very, very special. We use KSEG1 to address devices. And it's not going to make a lot of sense to you today, but as we continue in the coming days, it will start to make more and more sense as to exactly how KSEG1 behaves. But KSEG1 is not really storing anything. It's simply there's a tiny range of addresses we use in KSEG1, and if we see those addresses, we know that we are trying to talk to a device. All right. Now, how do we manage this memory? So when you actually load a program and you have to create an address space, ideally what's going to happen is the kernel of the operating system needs to manage the available physical memory. It needs to say, oh, I have 1 gigabyte of physical memory to give out, and I see you are requesting 512 bytes. So you need some way in the kernel to manage the memory that's available so that when there is a request, a kmalloc, we can actually serve memory up, find the range of memory that is available, and give it to the process or whatever program has requested that memory. And ideally, when the memory is freed, we also need to be able to keep track of the fact that that memory has been returned to the system. There is a name for this magical data structure that is supposed to be keeping track of the memory that is available and is free, or is not free, and that is called a core map. And OS 161 does not have one. There's none. OS 161 keeps track of virtual memory or available physical memory in the following way. It has a pointer. The pointer is the address where it is free. And when you make a request, it advances the pointer. And when you free, it does nothing. So every allocation, you're just moving the pointer a little bit more this way, this way, this way. And you know why you can't run tests back to back? Because the pointer runs out of memory. And we never actually give anything back. And on assignment 3, the big part of assignment 3 is for you to actually implement a core map so that OS 161 can actually do proper memory management and, free memory. Right now it does nothing. All right. Now, some interesting things. So, physical memory in OS 161 is divided into frames. So we are actually going to logically divide physical memory into frames, and we are also going to logically divide user memory all into pages. Now, even though OS 161 does segmentation for its virtual memory implementation, the actual MMU and the actual implementation of memory in the hardware uses paging. The reason why OS 161 is able to shove segmentation down the throat of a paging MMU is how it actually does the allocations for each segment. Ideally with paging, if your segment takes 7 pages, you can choose any 7 available pages for that segment. OS 161 says no, must be a contiguous block of pages. So we have segmentation math, but it's also technically paging underneath. You'll fix that again later. So technically speaking though, because we are using pages and frames, and our MMU is a paged MMU, it also has a TLB. What we actually see is that the user memory is actually going to be using paging and a TLB, so we are caching those results. All right, so that you've already seen. What about these kernel segments then? How do we actually do the translation? All right, here's how we do it. If you are kseg 0, it is not paged, and it is not cached. We're going to use dynamic relocation to do our address translation. All we're going to do is we are going to subtract from kseg 0 addresses the beginning of kseg 0. That's it. That's all we do. Whatever the kseg 0 address is, subtract the beginning, which is 80000000, subtract that from it, and you've got your physical address. We're done. What that means is that kseg 0 maps to the first 512 megabytes of physical memory. Now, does that mean that the first 512 megabytes of physical memory can only be used by the kernel? No. That is just the maximum amount of memory that the kernel could use. As I'm sure you've noticed, when we run our OS 161, we don't give it 512 megabytes of memory. We give it more like 512 kilobytes of memory. It's because the kernel doesn't need even a fraction of that space. We're just saying the kernel can use up to this much memory. It will use what it uses, and whatever is left can be used by the user program. So the leftovers can still be used by others. All right. What about kseg 1? kseg 1 is a magical segment that is not actually used to really store anything. It's simply used to address things. And it's technically a 512 megabyte segment within the virtual address range. But I can tell you that we are only using a range that is, what is it, 64 times 64 kilobytes. We're using a teeny tiny amount of it. And to do the address, if you see a kseg 1 address, to do the address translation, you subtract the beginning of kseg 1 from it. So the beginning of kseg 1 is going to be A0000000. And so if you subtract that value from any kseg 1 address, it gives you the physical address. Now, if you're sitting there doing the math, you probably just realized that that means that the physical address range that kseg 1 maps to is the exact same physical address range that kseg 0 maps to. You're absolutely correct. They both map to the first 512 megabytes of physical memory. Does that mean I have 2 things in virtual memory that map to the same physical address? No. We are saying in both cases, this segment can use up to this amount of memory. In practice, the region of addresses that we use for kseg 1 will not be used for kseg 0, and so it works out. It's obviously up to the developer to make sure that works out, because you can't have x equals 5 and x equals 7 in the same piece of memory. That doesn't make sense. So even though these 2 address ranges technically overlap, in practice, the regions that we will actually use are separate. Yeah?
Can you go back a few slides? Because like in the virtual memory part, next to the back line, what is the gray segment next to the user addresses in there?
The gray segment, kseg 2?
The one that starts at 0x0 and has six vertical bars.
Oh, that's just me drawing something to indicate that that's paged.
Oh.
Yeah.
Okay.
Nothing fancy, just indicating it's paged. All right, now of course, what do we use ksig2 for? Nothing, so don't worry about it. If the MMU sees a ksig2 address, it's going to throw a bus error. We're not going to transfer it. It's not too bad. All right, so I have a fun problem for you. I know, maybe it's not fun for you, but it's fun for me. Whew. Let's see what we got here. Make sure I get the right one. Here's the right one. So, this is a tricky problem. And if you've been paying attention, it's really easy. So, we're giving you physical addresses. And we want to know not which specific virtual address maps to that physical address. I want to know all of the possible virtual addresses that map to that physical address. That means there could be more than one possibility. So I'll give you the next 5 or 6 minutes, see if you can do it. No, see how you get it. How are you?
This is a physical address, right? So you know the virtual address is K60 like 8 hours. Well, there's all possible ones, right? More than one virtual address is only 2 addresses. And so you can start all of these by saying it could be a physical address.
Yeah, no, well, it was your solution. And that means one of them, one of your flags either A and then go back
Yeah, or at an age. I said C. I said
All right. So there's something very special about these physical addresses that we've given you. Does anyone know what is special about these physical addresses that we've given you? Here, let me tell you what it is. All 4 of the physical addresses we gave you live in the first 512 megabytes of physical memory. And we know that both kseg0 and kseg1 map to the first 512 megabytes of physical memory. It does not mean they are using it, it is just saying they map to it. And since all 4 of these addresses live in the first 512 megabytes of physical memory, I know that it is possible to have a kseg0 and a kseg1 virtual address for each of these physical ones. Keep in mind, we're looking at what are all of the possibilities, not what is actually true, which is what are all of the possibilities. So I'm going to use a regular expression here because I'm lazy. And I'm going to assume that you've all taken CS350 and know what a regular expression is. So for each of these, as I said, I'm using a regular. Alright, so there is a minimum of 2 possible virtual addresses for each of these physical ones. Now the question I ask you is, for any of these physical addresses, is it also possible that there is a user virtual address that maps to any of them? So for the first one, did anyone get a user address for the first one? See a few people saying, there is indeed one. How we know this is we're going to do a reversal lookup. So instead of doing a lookup based on page number, I'm going to do a lookup based on frame number. And when I get that, I realize, oh, yes, this first physical address could also have come from a user. And that one you should have gotten. So make sure I get the right number of X in here. So that's a possibility. How many of you got for number B a user address for that one? A few people. There's indeed a user one for that one as well. Did anyone get a user address for C? Because there is none for C. How about D? Did anyone get a user address for D? I see more hands that get it. Alright, so for that one, you should get, not A, 1, 0, 0. So there are all of the possible, excuse me, virtual addresses that we could have mapped to the physical addresses that we have given. Now, in reality, obviously, if you're using this for kernel or for the user, we're probably not using this as kernel app tracks. But this is not asking you exactly how it's being used. It's saying what are all of the possibilities. All right. Any other questions about these translations? Okay. Yeah.
So those remaining 3 gigabytes are only unavailable to the kernel, right? Like the user pages can still map to those 3 gigabytes.
Oh, those remaining 3 gigabytes? No, they're not used.
Like by the user or the kernel.
The system does not support it. OS 161 does not support more than 1 gigabyte of physical memory.
Okay, so if any of these are past the first gigabyte,
Then it would be an error.
okay.
We simply can't use them. All right. By the way, one of my favorite final exam problems is I love to give you a panic message and get you to tell me what's wrong. Here's a TLB panic unload. And I give you a kernel or a virtual address and a fault address, and you have to tell me whether it's a user or a kernel program and what was happening. And then how would you fix it? That's one of my favorite things. And why do I like that particular kind of question on a final exam? Because you have done so many assignments, and I'm going to guess and say that on A2A, A2B, and probably A3, you encountered TLB misses. So you should be pretty experienced with them. And in combination with our understanding of how virtual memory works, you should be able to figure it out. Favorite kind of problem. All right, so what I'd like to do then is to move on to the last section of virtual memory, and that is to finally actually talk about on-demand paging. So here's the thing. Right now, what we are doing is called address space preloading. So when I open a program in OS161, I am going to find the exact amount of memory I need to load the entire address space into RAM right now. And if I'm loading MATLAB, which needs like 5 gigabytes of space, that means I'm loading all 5 gigabytes of MATLAB's address space into RAM right now. Now, there are some advantages to this particular strategy. If I do address space preloading, it means that every single thing I could ever want that is a part of that program's address space is there in memory. Fast access. Well, it's reasonably fast access. It's great. But here's the problem. How much of MATLAB do you actually use when you start it up? The components of MATLAB that I tend to use are least squares fitting and matrix multiplication and the image library. So Simulink, yeah, I'm not using that. All the stuff to do biology, I'm not using that. So you're telling me that of the 5 gigabyte address space that I just loaded, I'm using less than 512 kilobytes of it? That's kind of a waste. Another way that you could think of this is when you install an operating system, whether it's Linux or whether you're using Microsoft Windows, a large part of the code base for those operating systems is not actually the kernel code itself, but is actually all of the driver code for all of the obscure little pieces of hardware that they believe that you might actually want to use. So Windows has a Dvorak keyboard driver in it, even though like a fraction of a fraction of a fraction of a percent of people even know what that is. And they've got sound card drivers that go back to when I was a child, so long before you were born. And they still support these legacy hardwares. So if we did address space preloading for Windows, then I would be loading gigabytes of drivers that I never use. Makes no sense. They'd all be right there and ready for me to use. But I tried the Dvorak keyboard thing when I was a kid, and it confused the hell out of me because I didn't know what it was. I found a weird floppy disk that said Dvorak keyboard, and I was like, ooh, this sounds like a game. And yeah, it was a game. I mean, it was a game in the sense where I was trying to figure out what letter was where, but that was not fun. So you do this address space preloading. You've got all of these drivers loaded, but now your operating system is taking gigabytes of space. If we actually look at what parts of the address space we need, it's significantly smaller than the total address space that we could load. So realistically, if we actually do address space preloading for large programs like an operating system or MATLAB, we end up loading into RAM gigabytes of additional things that we are never going to touch. And that just doesn't make any sense. Because if we do address space preloading where the whole address space has to sit in RAM, then because of how much memory that program is taking, it's actually restricting me from running other programs. Because there won't be as much physical memory left to run them. What makes a lot more sense is to only keep the address space components that we are actively using in RAM and keep everything else on secondary storage and only load it if we need it. And in many cases with things like Dvorak keyboard drivers, we're never going to need it. Although, just out of curiosity, does anyone actually use borax? How many of you know what I'm talking about? Wow, that's a lot of people. I'm sorry. All right. So what we're going to do is we want to exploit secondary storage. What we want to do is we want to be able to keep components of our address space on disk instead of keeping it actually in RAM. And this is going to give us a lot of extra functionality because now my whole address space doesn't need to be in RAM. That means that I have less of a burden on RAM, which means I can run more processes than I would normally be able to run. And it also, since I don't need the whole address space loaded now, it means that I can even run a program who technically needs more RAM than I actually have available. And we get all of this through exploiting our secondary storage. Now, of course, there's going to be a problem. We still have a finite amount of physical memory available. And there is a possibility that you opened up 200 copies of Netscape and you ran out of physical memory. So you are going to have to play the cache swapping game. When you run out of memory, you're going to have to choose somebody to kick out and insert yourself in. Sorry, the Netscape game is a prank I used to play on the librarians in high school. Admittedly, it was two. How many Netscapes could you open running Hamster Dance before the teacher went crazy? It's not that many. And if you've never seen the Hamster Dance, that's your homework. Don't find the modern one, find the traditional one. Maybe I'll just post it. All right. So here's one of the issues we now need to handle. So we now have this thing where part of our address space is now living not in RAM, but actually on the disk. So I need some way of keeping track of the fact that certain components of my address space are not present in memory. And how we do that is we add a bit to the page table entries. It's called the present bit. And the idea is that if the present bit is 0, it is not in RAM. And if it is not present and not in RAM, it has no frame number. Because it doesn't live in RAM, therefore why would it have a frame number? If, however, the present bit is 1, it means that it is in RAM, and we do have a frame number. Now, some interesting things. It is possible to have things that are valid but not in memory. Because we have ranges of our address space that are technically used, but simply not in memory right now. So you can have the valid bit be 1 and the present bit be 0. You can also, of course, have the valid bit be 1 and present bit be 1 because it is valid and it is in memory right now. But if the valid bit is 0, we don't even care what the value of the present bit is because it's not a valid address mapping and that's not changing because there's nothing there. Some interesting things. How about TLB entries? Should we have an entry in our TLB that is not present in physical memory? Doesn't make sense, does it? So one of the things that we also tend to keep track of when we're doing on-demand paging is in addition to the present bit, when we are making changes to the TLB or changes to some page mapping's present status, we need to make sure that anything that is not physically in memory right now shouldn't be in our TLB either. Because if it is in the TLB but it is not in RAM, then it doesn't have a frame number. And if you don't have a frame number, then you can't actually do the address translation. So why are you in the TLB? TLB is supposed to be fast, not garbage. So if you're in the TLB, you should also be present. Yeah?
If you only have one page in physical memory, how does that represent in TLB?
If you only have one, like, what do you mean by one page? Like, all the physical memory is one page? Or do you mean, like, we only actually use one page?
We only use one page in physical memory.
So if we're only actually using one page, then it would just be a regular TLB entry.
And then, what about, does the TLB also have a valid bit?
Well, the TLB, page table entries have a valid bit, and in fact, the MIPS R3000 TLB does also keep a valid bit. it's one of those things where I kind of think it's pointless because you should only let entries go into the TLB that are valid in the first place. But technically speaking, the R3000 TLB does have a valid bit as part of it. I think if you're looking at it, it actually kind of maintains a certain, it looks like a regular page table entry. So it actually contains a lot of things that we could use but we don't use. For example, it contains a PID, which is not used in MIPS, but it's there.
Okay, I'm just trying to come up with a hypothetical scenario where your TLB only has a 1,000 entry.
The very first thing you load. So you've called AS activate to clear out your TLB, and then the very first thing that you start reading adds one TLB entry to it.
Okay, and what is the remaining part of the TLB?
If there is only one entry in the TLB, then the remaining elements would be marked as empty.
Okay.
Yeah. All right. So we now have a new kind of problem that comes up. So before we had things called TLB misses, which is when we tried to do a page to frame mapping and we checked the TLB and realized, oh wait, it's not in the TLB, so maybe I better get that fixed. Find the TLB entry, add it to the TLB. And we used the software managed TLB, so we threw an exception, and then the kernel, found the entry for the page table, and then it added it to the TLB, and maybe we evicted an existing element. Software managed TLB, very calm. We have a new kind of exception, and that is a page fault. A page fault is we need to perform an address translation, but we can't because the page is not actually present in memory right now, which means we can't do a translation because we have no frame number to do the translation. We can't even access the memory on the page because it's not even there. And what's interesting is that we detect page faults in our software managed system through TLB misses. Because again, we should not have entries in our TLB that are not present. That doesn't make any sense. So what's going to happen is we get a TLB miss because the page table entry is not in the TLB. It's going to throw an exception and the kernel is going to respond to that exception. When we are trying to address the exception raised by the TLB, that TLB miss, we are going to first check the present bit. We find the page table entry and we check the present bit. If the present bit is 1, then we just update the TLB as normal. But if the present bit is 0, that's where things change. If the present bit is 0, and we've gotten TLB miss, it doesn't mean TLB miss, it also means page fault. And on a page fault, we have to find the page in memory. We actually have to find a physical frame to put it. And if there are no physical frames available, then we have to kick somebody out so we can go in. Once we have put the memory block into physical memory, we now have a frame number, which lets us update the page table entry. We change the present bit to 1, and now we update the TLB with the new page table entry. We retry the address, and it works the second time around. So we detect page faults through our TLB misses. Okay. Now, does this have an impact on performance? Yes, unfortunately it does. So one of the advantages of doing address space preloading, which is we don't keep anything in secondary storage, is that 100% of the address space is in RAM, which means that we can cache things. We never have to do anything that's slower than accessing RAM. The downside of on-demand paging is now parts of my address space are not living in memory, they're actually living in secondary storage. And secondary storage can be orders of magnitude slower than accessing RAM. Because you've got your CPU, and accessing anything in the CPU is pretty quick because it's very close together and very fast. And then if you want to go to RAM, you have to leave the CPU and go along the bus line over to RAM and then back. It's a short distance, but it still takes time. And if we're now talking about, okay, now you want to go to the disks, you are leaving the CPU, you're leaving the motherboard, you are traveling along potentially very long wires to a secondary storage unit, and if that is a magnetic tape drive, I'm being a little extreme here, you've then got to grab it from there and pull it all the way back to the motherboard, and through the motherboard all the way back to the CPU. orders of magnitude more time to grab stuff from secondary storage. So here's the problem. How often we encounter page faults that require swaps is actually going to impact our performance significantly. Yes, we get all these beautiful good things like being able to run more processes than we have memory for, and being able to run a process that needs more memory than we technically have. But we have a performance hit. How much? So if I have one page fault that requires a swap every 10 memory accesses, 100 times slower than address space preloading. And you might be thinking, oh, that means like once every 10 instructions? No. That could be less than every 10 instructions. It could be a lot less than every 10 instructions. That could be as few as like 5 instructions. So it's pretty nasty. If we have one swap every 100 instructions, then it's 10 times slower. And if we have one swap every 1,000 instructions, or sorry, every 1,000 memory accesses, then it's twice as slow. These are very, very expensive. So when we're dealing with something like on-demand paging, what we really want to do is find some way to minimize the number of times that we're actually going to have to do swaps. I want to make sure that I am balancing the advanced ideas that I get from on-demand paging, like running more things, with the slowdown. Now, how could we solve that problem? Well, there's two ways that we can solve this problem of swapping. We can do prefetching. So we can predict which page is the address space we're going to need next, and we can preload them so that when we actually do need them, they're there. That's not interesting. So we're not really going to talk about it. But for the record, it's not in the notes. Address space, or the prefetching on some more modern CPUs, like the new Spark chips that have something like 32 cores or 36 cores, they actually have 2 cores completely dedicated to operating system related computation, which means that you could technically use an entire core to do prefetching while the programs were actually running. So that's actually really cool. And some more, server-esque high-performance computing actually have dedicated cores for prefetching. We don't do that. We could, but the problem is for a general-purpose CPU, in order to do prefetching, I would have to take time away from the user's program in order to do it. So we aren't going to talk about that. The other option is just be smart about things. Be smart about which pages you are evicting from physical memory. Be smart about page swapping. And that's actually where the interesting algorithms come into play. So that's where we're going to spend the rest of this time. So we're going to look at page replacement policies, and I want to tell you that we're talking about this in the context of my memory is full, I need to bring something from disk into RAM. These are all, technically speaking, cache eviction strategies. It's the same idea. So the easiest way to do this is called first in, first out. So we always evict the page that is oldest, the one that was first. We'll kick it out first. So what we have to show you how this works, and I apologize, these examples in the notes aren't necessarily the best. So we've got some memory references here, and so we've got A, B, C, D. That is the page of memory I want to reference, and then the number is which number, the order in which we are accessing them in. And my RAM, to make sure we get some page faults here, we're only going to have 3 frames. Tiny RAM, 3 frames. Awesome, right? All right, so when we start out with FIFO, we have nothing. That means it's actually page faults, because we haven't actually loaded our address space into memory. So on the first memory access, we get a page fault. And, oh, look at that, there's free space. So we load A, no problem. And the same for B and the same for C. Each time we access them the first time, because they weren't preloaded, they're going to cause that page fault. Once they are loaded, however, and we have all 3 frames filled, Now we start to get things going interestingly. So in memory access 4, I try to read from page D. And here's the problem. My memory is full. I have A, B, and C are occupying the 3 frames that I have. So I'm going to have to kick somebody out in order to load D and actually use something on page D. So I've got to choose somebody to evict. FIFO says first in, first out. The first one in was A, so I evict A. It's a fault, I load in D, and guess what happens the next memory access? I try to access A again. Oops. And so, well, now I've got to choose who's the one I'm going to evict. Well, B is now the oldest one, so I evict B. And then, of course, immediately after evicting B, I'm going to use it again, right? While first in, first out is very fair, and it's very easy to implement, in terms of minimizing the number of page faults that occur, minimizing the amount of swapping, that's not it. It's not great. What is the best that we can do? What's the best algorithm? Let's jump to the ultimate solution. Do you know what it is? No. The best possible algorithm, the ultimate optimal page replacement. You evict the page that you're not going to use for the longest period of time. So, we still get a fault on A, we still get a fault on B, we still get a fault on C as we're loading things in, but when we get to D, we have to choose one of A, B, or C to evict. Well, at memory access 5, I see I'm going to use A again, so that's not good. And I'm going to use B again immediately after, so maybe I don't want to evict B, but look, I don't use C until access 10. So let's keep 10 out, or C out. Is there a problem? This is impossible. I don't know the future. Your computer doesn't know the future. I'm going to make the assumption that you don't know the future either, unless one of you is like some magical quantum being or something. Yeah.
What if I'm on a GPU and I'm not expecting any branches? Then, can I see the future?
If you're a GPU and you have no branches, can you see the future? No. Because you're assuming linear access to memory, and even though our instructions with the GPU would go in linear order, obviously for many reasons, the individual memory accesses may not be linear in nature. They could actually be accessing random parts. It's just the instructions have to. This is not possible. We can't do this. We don't know the future. So you can put a big X through this. Nobody here is a psychic, I presume. All right. But we can take advantage of something called locality. There are some basic things that we know. One of them, they're called spatial and temporal locality. So if I am executing a program that's, add sub, add sub, add sub, just a bunch of instructions in sequence. Well, things that are in sequence like that, well, they're probably on the same page, right? Or they are on pages that are very close to each other. Things we have accessed recently, we are very likely to access again, especially if you think of the fact that if I'm executing a sequence of instructions, then I'm probably using the same rough spatial area again. And the same is true for temporal. Things that I have used recently, I'm probably likely to use again. If I am trying to access an image, and I'm using each of the pixels of the image, well, then I'm probably likely to need to access the image again. So can we take advantage of locality to improve our cache eviction algorithm? All right, so least recently used as suggested, let's look at that. So in this case, I'm going to evict the page that was least recently used. Not the oldest one, the one that was least recently used, and they may be different. Now, unfortunately, in this example, it's roughly the same as FIFO. bad example on our part, but it could happen, you know. So A, B, and C, the first times those are all page faults. When we get D, and A, B, and C, which was least recently used, well, that was A, so I evicted A. And of course, it didn't pick up on the fact that, hey, I'm going to use A again. Again, bad example. And then when I've got to choose from D, B, and C, least recently used there is going to be B, so I evict B. We use it right again. All right. In practice, however, you do get better behavior than what you're seeing here. Now, my question to you is, can you implement this? Is it practical to implement this? Not practical to implement this. So here's the question for you. Who does address translations? The MMU does the address translations. Every successful address translation, the kernel doesn't know about it. Least recently used needs to know about every recent successful use of an address translation. I.e., I need to know when that page to frame mapping was used last. My MMU doesn't have a timestamp that keeps track of when each TLP entry was used last. That's not practical. I would need more 32 bits extra per mapping. I would need the MMU to know about the clock. That's a pain in the ass. Could be done, pain, not gonna do it. So if the MMU doesn't know when the least recently used thing was, the only person who could keep track of it is the kernel. But the kernel only knows about unsuccessful address translations, which means it doesn't know anything about the successful ones. So in practice, it is impractical to implement least recently used because we don't alter our hardware to suddenly know time, and we don't want our kernel involved in all the successful address translations because then we might as well not use an MMU at all, which would be really bad. So least recently used sounds like a great idea, but practically speaking, we can't really do it. It doesn't work out. So we can't add to our MMU a clock because that's not practical. And we don't want to add to our MMU, you know, a great big field for time. But we can add a bit. A bit is okay. A bit's not bad. A bit is just a bit. It's one bit. It's just one bit. We can do that. So what we have is a use bit. And it's in each page table entry. And what's going to happen is that every time the MMU performs a translation on that particular page, we are going to set the use bit to 1. And then periodically, the kernel will take all of the use bits and reset them to 0. So we're going to use the use bit to indicate, has this address translation been used since the last time the kernel cleared it out? So we are not keeping track of the exact time that it was used. We're just keeping a rough idea of, since the last time the kernel cleared all this out, has this address translation been used? We will use this strategy then to implement something called the clock algorithm to keep track of what's roughly been used recently. So the clock replacement algorithm. Now, yes, we've got this example here. Again, it's a bad example. I don't know how they did it. They managed to find an example that is like bad for everything. That's like amazing to find something that's bad for every algorithm. And we could go through this pseudocode here, but I don't find the pseudocode particularly useful. So I'm going to switch to the board and walk you through what happens with the clock algorithm. Alright, it's called the clock because we are going to go around in circles. So instead of drawing RAM the way it's actually, like a sequence of RAM, we're going to draw RAM now as a clock, a big circle. So here is RAM now, and let's give it 8 pages. So here's RAM. And now, just to keep things simple, I'm going to put the use bit in this inner track, like so. So there's the use bit, and let's say I've got, I don't want something in there. Let's say that my RAM is full. I've got something in every single slot. All right. I also keep track of something called the victim pointer. Here's what happens. So we need to do a swap because I'm trying to load a page in. I had a page fault and memory is full, so I need to do someone to evict. I'm going to look at the victim pointer and I'm going to check that translation that we're using there, that page table entry. I check its use bit. Its use bit is 1, which means since the last time it was cleared, it was used. I don't know how recently that was, but I know it was used. So this is probably not a good choice of somebody to evict. So I'm not going to use this one, but I am going to keep track of, does this get used again? And I'm going to set the use bit to 0. And then I advance the victim pointer to the next slot. And I check the use bit and I see that it's 1, probably not a good choice. So we'll set the use bit to 0, and we advance the victim pointer here. We see again that it's a 1, so we're going to reset it to 0 and advance the victim pointer again. And now I found a victim whose use bit is 0. That means that since the last time it was cleared, it wasn't used, which means it probably hasn't been used recently. This is a great choice to evict. So I'm going to evict D, and I'm going to insert S, and I'm going to advance the victim pointer, and now I have the memory is actually in RAM. I add it to the TLB. You'll note I don't set the use bit here. The reason why I haven't set the use bit yet is immediately upon inserting S into the slot and adding it to the TLB, we are going to retry that address translation. It's going to succeed, which means the MMU is going to set it to 1 for us. So there's no reason for us to do it. So we let the MMU set it to 1, and it succeeds. And then the next time I have a page fault, I start with wherever the victim pointer left off. So it left off here, I would set this one to 0, and I end up taking F out. Now, you might wonder, what happens if I use every single address? What if they're all 1? What if the use bits are all 1? Why not just keep going around in circles? No, you don't. Because when you try to victimize an entry and realize it was used, you reset its use bit to 0 so that you can keep track of does it get used again in the near future. Which means that after you have traveled from your starting position back around to the start position again, i.e. 1 full cycle of the clock, when you come back to the initial position you were in, the use bit was reset to 0, which means that you end up victimizing it and you stop. So it doesn't go on forever. This clock algorithm is something that we can implement because we only need to worry about unsuccessful translations. And is it perfectly accurate? No. But it's as pretty good as we can do. Now, this is not just, by the way, we're using this for swapping memory for RAM. You can use this for cache evictions as well. And I know when you get excited about A3, I know you haven't started A2B yet, but when you get to A3 and you realize that OS 161 has no cache eviction strategy for its TLB, i.e. it panics when the TLB is full, And you're going to be so tempted to like, oh, we need to implement clock for the TLB. Don't bother. It's too much work. We just want you to do random. All right, so that's it for today. Have fun.